Yeah, this should take us probably 20 minutes, half an hour, I think. So we're going to start with history again, because I was joking with somebody earlier today. You thought you signed up for a physics course, but it's kind of half social studies right now. So here's one more scientist that I need you guys to know a little bit about. His name was Charlie Wilson, and he built what's called a cloud chamber. He's not on your list, by the way, to do for timeline. He was a relatively minor scientist. He built a cloud chamber, and you guys can read the story here. The bulk of the important stuff is that he ionized some molecules, causing water vapor to condense. He found some charged particles, and they kind of looked like, you know how when an airplane goes through the sky, how you can see the vapor trail behind it? My kid goes, oh, look, there's the airplane, right? Well, he found a way to get in this cloud chamber some charged particles, and he didn't know what they were. Again, this is 1894. Think about the context. In 1894, did they know about nucleuses yet? Nope. I think we're only just talking J.J. Thomson's experiment was right around that time as well, right? So he found these particles that he had no idea what they were, and they behaved very strangely because he found the charge to mass ratio. So he discovered the charge to mass ratio, and they were the charge to mass ratio of an electron. But when he put them inside of a magnetic field, where did I write that? Where's the magnetic field? Here it is. When he put them inside of a magnetic field, they actually spun this way. I had to use my hand to do this one properly. If they're spinning this way, that was actually a positive particle that would spin this way, because a negative particle would spin this way. And that really confused him. We actually know what this particle is, though. It's called a positron. It is an electron, essentially, but rather than having a negative mass, a negative charge, it has a positive charge. So to begin today's lesson, I actually want to review some of the things we talked about in previous lessons, the alpha and beta and gamma decay. I think we should review those real quick. So let's begin with alpha decay. Let's say you have some random unknown particle, and it's not really all that stable. Okay. It really wants to break apart into pieces. I'm just going to pick some random numbers here. Let's make this number 180. Let's make this be the number 87. If it's going to undergo alpha decay, what you basically do is you just kick out 4 particles. The 4 particles in an alpha particle are 2 protons and 2 neutrons. And we draw it like this. This is an alpha particle with a 4 and a 2. You should then be able to predict what it's going to make. It's just basic math. 180 minus 4 means the top is 176, and 87 minus 2 means the bottom's 85. I have no idea what this element is, but you're given a periodic table, so they might ask you to look it up on the periodic table. In terms of terminology, this thing is called the parent, and this one right here is called the daughter. That one didn't probably confuse too many kids. That one's okay. But then there came along beta decay, and beta decay was really weird. I'll use the exact same random element I started with, 180 over 87. In beta decay, what ends up happening is you spit out what was called a beta particle, and the form of matter that you had actually went up from 87 to 88. And somehow a proton was gained, because here's what occurred. A neutron split into an electron and into a proton. And we have some evidence of this. We're actually going to further this evidence with some notes today, but the mass of a neutron is actually a little bit higher than the mass of a proton, because it's believed that somewhere embedded inside of it is an electron, kind of. We're going to talk about that today. So here's the problem, though. As these things split up into pieces, what ended up occurring is that the daughter nucleus would go one way. Like here's your original piece. The daughter would go one way. The electron, which was basically your beta particle, the -1 and the 0, would go another direction. But conservation of mass and momentum, it didn't really seem to fit all that well. And this electron was traveling too slow. And eventually scientists discovered this particle, which we use a V with a line over top of. They called it an antineutrino. And it was the first evidence of, first of all, both something known as antimatter, which we're going to discuss today, as well as evidence of the subatomic particles. They don't actually use the word subatomic particles. They use the word quarks, which is one of the, is that the title of my lesson? What did I call it, today's lesson? Yeah, quarks. So we're going to discuss today basically the idea of what the heck is that antineutrino? And if after today's lesson you still feel like you don't actually know the answer to that, that's okay. I still don't really fully get it, which is frustrating and so cool at the same time though, because this is what scientists are working on, trying to figure out what is the smaller stuff made out of. It really wasn't until a few years ago that the Higgs boson particle was finally discovered. So I'm going to fast forward in my notes a bit here to this slide right here. Current scientists, I mean, if you are like a top of the line particle physicist, you're probably working at this location. Does anybody know where this is? It's in Switzerland. This is the CERN, C-E-R-N, super collider. It took like decades to build, and scientists have only just started being able to use the CERN super collider. It's in Geneva, Switzerland. And basically what's happening is they built like one really, really, really massive track in a circle. And my guess is there's probably a very powerful magnetic field underneath it so that it causes the particle to bend in said circle. And you've got a second one over here. And the same thing's going to occur here. There's probably a massive magnetic field underneath it causing a particle to go around in circles. And as it does it, they speed them up faster and faster and faster, until eventually what they do probably around this location right here is that rather than it bending around the corner, maybe yellow will show up, there we go. Rather than bending around the corner and bending around the corner, they eventually let them hit each other. With the theory being that if you smash an electron into another electron, maybe you'll find the subatomic particles. What is smaller than an electron? And if you guys have heard of something called string theory, that's called kind of like the end game. The ultimate goal is that if we could just keep going smaller and smaller and smaller, there's a theory that everything in the universe is made up of vibrating strings. I don't get it. If I did, I wouldn't be teaching here, right? You guys understand that, right? So I have no shame in saying that, like, I don't fully get this stuff. I don't even expect you to. We're just teaching you like the basics. And if you love this, go on and learn more about this, because it's what modern physicists do. So anyways, that's a particle accelerator. So if I can go back in the slides a little bit here, scientists were basically, physicists were discovering these other parts of matter that were smaller than the typical particles. And they were also finding antimatter. They were finding things like how electrons had an opposite doppelganger called a positron. They were discovering how protons have a doppelganger called an antiproton. These things have the same mass as each other, but they have the wrong charge. In my mind, I think of like a bad doppelganger twin who, like, the one is the normal person and the other guy has like a bad mustache. You know, it's like in some sort of comedy movie where you put on the mustache and all of a sudden now that's your evil twin. I don't know, that's what I kind of think of here. Now, this one right here is the one that I really don't get. Apparently, they've discovered a neutron and an antineutron. And I don't fully get, how can you have an antineutron? It doesn't even have a charge. I'm actually not sure. Here's what I do know, though. They've actually discovered that when matter and antimatter collide, particle-antiparticle annihilation occurs. And you actually get energy out of this. So the reason why I do believe, like, it's not like I don't trust the scientists out there, but the reason why I believe that there is such a thing as an antineutrino is that if you ever brought a neutron into contact with the antineutron, they would actually literally vaporize each other and make pure energy. And this is actually the theory behind what physicists believe happened during the Big Bang. They believe that when the Big Bang occurred, there was some matter and there was some antimatter, and that it collided. And in doing so, the matter and the antimatter basically exploded into energy. But in the aftermath of that, there was actually more matter than antimatter, which is why we have our stuff. Because, like, we're made of particles, right? There's matter here, matter there, matter everywhere, right? There's also energy in our universe. So the thought is matter and antimatter collided. And you guys can see I'm using a different number of fingers, right? Because there was this annihilated each other, made energy, this made energy, this made energy, this made energy, but there was just enough left over for there to be stuff, matter, for our universe to exist in. And that's kind of the theory behind the Big Bang Theory if you want to research that some more. So, long story short, there's weird particles out there that have like antimatter properties. I wish I could tell you more, but I really don't know more than that. So. Okay, in the 1930s then, physicists began to call this the subatomic zoo. I love the phrasing of that because it started to get so weird and crazy as they were finding these new random particles. So not just protons, neutrons, and electrons, but neutrinos, antineutrinos, positrons, antineutrons. They eventually started calling these things quarks. The word quark is what we kind of use to describe, like I said, the subatomic particles. And here is basically a summary of what they've discovered. You do not need to memorize this because all of these are listed on the back of your formula sheet. So if you guys have a formula sheet nearby and you look on one side of it, there's a chart on there. Zainab, isn't it like the bottom right-hand corner? Is that where there's a chart there? No. Yeah, on the right-hand side, is there a chart that lists like things like this? Electrons, muons, tauons, pions. You find that there? Okay. So you don't have to memorize this chart because it's listed for you there. And I've been teaching physics for a while. I have really not seen a lot of diploma questions on this topic. I actually can't think of any, truth be told. So I'm hoping that they won't assess you on this. That'd be great. But you basically just need to know that there are smaller things out there than protons, neutrons, and electrons. They're actually going to list their masses in a weird unit. This may come up. I want you guys to know how this works here. The mass of these things, can you see how it's been listed in MeV over c squareds? That is a weird unit. Here's why. What's the mass of an electron? 9.11 E minus 31. And for the longest time, that's what we thought was the smallest thing out there. For a while, we thought hydrogen was the smallest thing. And then they discovered corpuscles, or electrons. Okay, now that's the smallest thing, right? But look at this chart here. The electron's actually the biggest thing on this chart. Well, more or less, right? One of the bigger ones on this chart here. And so we needed a new unit to describe things. And so what they've done is they've taken the formula E equals mc squared, and they've isolated for mass. Right? So if you rearrange this for mass, you'd now get E over c squared. But rather than putting energy in joules, they've put energy into electron volts. Technically, it's a mega electron volt, so that's 10 to the 6. But then they're dividing it by the speed of light. And so now they're getting still a unit for mass, but it's not in a typical kilogram number. It's now in like these numbers here. The reason why these are preferable, though, if I had to actually put this into kilograms, it's probably something to the power of like -80, which is just so incredibly tiny that it gets kind of dumb after a while. Does that make sense? So one thing I would like you guys to be able to know is that if they give you MeV over c squared, that's a unit for mass now. So, and I've got notes on this on the slide here. So most of these particles being discovered, they're only in existence for a few microseconds. Again, how do we get these particles? We smash electrons into each other at high speeds, or we smash protons and neutrons into each other at high speeds, right? Hoping that they will break. So measuring them in kilograms is kind of ridiculous. So this is the unit. Does that make sense? I have no idea how they would even assess you on this, honestly, because there's not a lot of examples that I can give you from the past where they say, here's what they used to do. So yeah, go ahead. So I'm just trying to cover my bases and just, you know, if this comes up, hopefully we've talked about it enough. So in the 1960s, physicists are still confused. They have no idea really what these things are, so they broke them up into two groups. They broke them up into something called leptons and hadrons, where the leptons seem to be smaller, and the hadrons are kind of bigger, but they're still small. Okay? And the real difference is that leptons, where's this note here? Leptons, here, I'm going to go back to this one here. Leptons, they've only discovered 6 leptons, as well as their antiparticles. Okay? And what's weird about these things is that we can measure them based on how they spin. Do you guys recall that one video I showed you where Einstein and Bohr were debating about spinning electrons? They've discovered that we can measure these things based on their spin, whereas these things, there's like hundreds of them having been discovered. You can't even keep track of them all. So, where was it here? So we believe that these things are made up of these subatomic particles called quarks. This is the one thing that I have seen them assess on, the idea of what's called fractional charge. We talked about Robert Millikan and how he did the Millikan oil dop experiment and discovered that the smallest charge you could possibly have was 1.6 e minus 19. Well, we now think that's wrong. So I've kind of been lying to you for the last 3 months. Right? We thought that the elementary charge of 1.6 times 10 to the minus 19, we thought that was basically as small as you could ever get. We now believe that there are things known as up quarks and down quarks, and anti-up quarks and anti-down quarks. And these are like the smaller little pieces. And honestly, the best way I can describe this to you is with a picture. So here's a picture. This is what scientists believe a proton actually looks like if you could somehow look at it. This is a picture of what they think a proton is. Why do we think it's a proton? Well, because it's got this thing right here known as an up quark. And it's got a partial charge. It's not a full charge. They think that it's got 2/3 of a charge. And here's another one. It's got 2/3 of a charge. What's 2/3 plus 2/3? 4/3. That's over 1, right? But it also believes that somewhere hidden inside a proton is a small negative charge. I know, right? Like, you give me funny looks. I have the same funny looks. So they believe there's a partial electron hidden inside here, right? But isn't 2/3 plus 2/3 4/3? Take away a third, isn't that going to give you 3/3? And here's the evidence they had for it. They shot some electrons near a single proton, super, super close, like as close to the nucleus as you could possibly imagine. And what ended up happening is some of the electrons actually bent in towards this proton. But that makes sense, though. Wouldn't a negatively charged particle want to get closer to positively charged stuff? That's logical. But here's what was weird. It didn't bend this way on the other side. It actually bent away on the other side because they believed that there was a negative charge. What would negative things want to do next to other negatives? They would want to repel. So there seems to be evidence out there that protons are actually divisible. And they're made up of things called quarks. And so these are on your formula sheet. I believe it lists the up and down and the anti-up and down quarks. And so the only questions I've ever seen asked about this would be something like this. If they told you that you had an up, and a down, what does that make, basically? And so if you go back here, an up is a plus 2/3, and a down is a negative 1/3. So if you had a positive 2/3, you had another positive 2/3, and you had a negative 1/3, what have you now made? You've made a proton. Let me try another one. What if I give you an up, down, down? It's a neutron, because an up is a positive 2/3, a down is a negative 1/3, a second down is a negative 1/3. Doesn't that basically neutralize each other and come out to nothing? Which kind of explains where I began one of our lessons here. I mentioned that there are theories that a neutron is actually made of an electron and a proton. And so if these particles here can be subdivided, then yeah, maybe you can somehow like reach into a neutron and like pull an electron out somehow. That actually almost makes sense. Did you have a question? Based on their partial charges. Yeah, I did say that, yeah. And that was kind of like a partial kind of truth, because really what we believe is that really all of these things, protons, neutrons, electrons, they're all made up of like partial smaller stuff, right? So the basic building block of life is no longer an element. And it's actually no longer a proton, neutron, or electron. It's actually these quark things. So based on that theory, maybe it's not really quite fair to say that a neutron is made up of a proton and electron, because there was also that antineutrino as well, right? But it's made up of these like little partial bits. And like this diagram here is really crude because I'm just kind of drawing like a circle within a circle. We can't see this, right? We can't zoom on the magic school bus and get closer and closer to it. This is like as small as stuff seems to be. So, do you have a question? Okay, that's a good point. So, do you have a formula sheet? Can I steal yours real quick? So on the formula sheet, I want to write out a few of the things it mentions. It gives the, let's make a new slide. If you have your formula sheet, try to follow along here. It mentioned that there is the up quark, which is a positive 2/3. It mentioned that there is an anti-up quark, which is a negative 2/3. It mentioned that there is a down quark, which is negative 1/3. And I mentioned that there is an anti-down, which is positive 1/3. I think I have those all right now. Yeah. So you know how a second ago I told you that if you had an up and a down, this made a proton? Because you have a 2/3, you have a 2/3, and you have a negative 1/3. Well, what if I used a negative up, and a negative down? What if I used all antimatter? Let's walk through what this would be like. An anti-up would be a negative 2/3. A second anti-up would be a negative 2/3. And a down would be a, where's my anti-down? A positive 1/3. What sort of charge will this thing have when it's done? If it has a negative 2/3, a negative 2/3, and a 1/3. Negative 1. What is this particle, though? It's not an electron. It's an antiproton. Yeah. And the reason why it's not an electron is that it has the mass similar to a proton. This weighs the same as this one. This weighs the same as this one. This weighs the same as this one. So mathematically, mass-wise, it actually weighs the same amount, and it seems to have the wrong charge to it. So this -1 charged particle is actually your antiproton, which is kind of weird. Now, I'm not 100% certain on this one because this is not my field of study, but I believe the way that it works is that an electron is perhaps meant to be like an up. No, what is it supposed to be? It's supposed to be like a down, and a down. If you had 3 downs, if you had all 3 of these, you might then have now an electron because you have 3 collective ones there. But the mass will be different than these ones here instead. So it gets kind of weird. And like I said, I have no shame kind of saying, look, I don't fully get this either. If I did, I'd be working at MIT. Right. So here's what I need you to be able to do. And let me find you an old diploma question, because you're giving me a funny look like, Chris, how am I supposed to learn this if you don't get it? Because I know, that's frustrating. Let me find you an old diploma question here. Let's do hopefully it's on the June 2009 one. Here we go. Take a look at number 40. It said a neutron and a proton can be modeled using quark combinations. Which row matches the quark combination for those nucleons? So this one asked for proton and neutron. Actually, we just literally did this a second ago, eh? Right. So a proton would need an up and a down, because that's 2/3, 2/3, back a third. And then the neutron would be the up, down, down, because this would be up 2/3, but then down 2/3. That'd be neutral again. Right. I know it didn't ask for it, but these ones right here, UDD and UUD, this must be the anti-neutron, and this must be the anti-proton. Right? Because they have the same stuff, just the wrong charge to them. So that is how they asked this question before on the diploma. I'm not really even sure how they're going to ask it otherwise, other than you just need to know the U's and the D's, and the U's with the line and the D's with the line. Okay. Here's my suggestion. Because this is such a weird and challenging section, and I can really only add so much to this whole missing charge little bit here, the last note I put in here is that I think it's actually worthwhile to read your textbook on this chapter. I know I didn't even have you guys get textbooks, but I think it would be worthwhile to maybe just sign one out of the or out of the textbook center, and go find like the last chapter in the textbook and just read it yourself, just in case it somehow helps to solidify this knowledge a bit more, because it's challenging stuff. Let me do my last slide and then I'm done, because I've actually covered what I need to for the day. We can actually explain a little bit about how the beta decay turned a neutron into an electron and a proton. Remember how UUD was supposed to be neutral? It's a plus 2/3 charge a minus 2/3 and a minus third and a minus third was neutral? Well, this is what a neutron is. A neutron is an up, a down, and a down. That's neutral. And a proton is an up, and a down, because this is +1 and this is 0. What do you need to do to change a neutron into a proton? See how this up right here is still up? That hasn't changed. This down right here is still down. It hasn't changed. What has to change? Apparently, and I'm not really sure how this works, but apparently a down quark needs to somehow get turned into an up quark. And if you can do that, you can then cause a neutron to become a proton. But now consider the charges. You went from having a negative 1/3 here to being a plus 2/3. You can't just all of a sudden gain some positive charge. So what would have to get emitted? An electron would then have to be emitted in order to change the down into an up. And somewhere in there, that antineutrino comes out as well. And this picture doesn't even draw in what antineutrinos look like. Now, somewhere in here, there's another little bit that got spit out somehow. So this is what modern physicists are working on. And clearly, they'd be able to articulate it way better than I am. But like, if you find this fascinating and you like this stuff, go into physics. Learn more about it. And if you think that this is like weird and stupid and crazy and like, why do we care what the smaller bit is and smaller than that, right? Like, this is what makes, any of you guys watch the show The Big Bang Theory on TV? If you have, Leonard and Sheldon, the two characters, one is an experimental physicist, one is a theoretical physicist. This is really where physics is at right now. There's a divide where there are some scientists who they just think of theories and they think, this is how I think the world works. But it's really, really, really hard to design experiments to prove that. And so there's always these two sides to it. A scientist does an experiment, and we try to figure out, well, what does it mean? Or a scientist says, I think this is the picture of how it looks. And they go, but how do you prove it without making an experiment to do that? So that's what makes physics, I don't know, I love it and I hate it. Because I wish I could tell you more, but like, I don't actually know more. Big sigh. Okay, so that's our unit. Let me summarize our unit, then I'll shut up for the day. This section here is mostly theory and history and social studies context a little bit. You need to know your scientists. Okay, you do. It's very likely that you're going to be assessed on like, what did Rutherford do? What did Bohr do? What did Einstein do? What did de Broglie do? And they will likely blur that science stuff together with like the previous unit for who did what. So I don't care about it for the mark point of view. I care about it for the learning point of view. You guys really should do a timeline. I think it's worth it. Okay, and even if you're like subdividing it into groups, make sure that at the end of the day you know who does what. Okay. In terms of formulas this unit, there's very few. You need to know how to do the E equals HF formula for electrons that bump up and fall back down energy levels. We're doing that in our activity the other day, where like an electron gains energy and then it falls back down and it emits a wavelength of light. But like, that's not a new formula. We've always used that formula. You need to know how to use the formula E equals mc squared. But again, that one's pretty straightforward. All you have to do is just find the difference in mass. The difference in mass times by the speed of light to get the binding energy, that glue. And the only other formula is the half-life formula, n equals n0, 1/2 to the power of n. If you want more examples of that, I can find you more. But I found the best way for me to get you guys prepared for this is to give you a practice quiz. So sometime early next week, I'm going to give you a practice quiz, and it is going to have more questions on it than I'm going to give you on your unit test. Because I don't need you to write it all in one day. I just want to give you lots of different, okay, here's what they've done in the past, so you get a sense of what you might be assessed on. For me, preparing you for this unit, this is the hardest one for me to prep you for, because there's like the least amount of old questions to go off of. There's not a lot of continuity. Like, I know for sure there is going to be 1 and 2 dimensional vector problems in momentum. I know that. I know they're going to test your left and right hand rules. I know they're going to test that. I know that you need to memorize your electromagnetic spectrum. There are some things that I can tell you, know this, there's going to be a question. On the diploma in this section, I really don't know, which is frustrating to try to help prepare you. So I'm really just trying to say, let's cover as many bases as we can. So, So here's your to-do list. Work on the one assignment, the one activity, like the lab we did the other day, and make a timeline. And sometime next week, write a quiz. After you write the quiz, write a unit test. And then we're done. After Christmas, we'll do retests, we'll do practice tests, and we'll try to get you ready for that diploma. Sound good? Yay, we're done the curriculum, everybody. It's a real weird way to end it, though, isn't it? Such a weird lesson. Okay, I'm done, guys. You guys are free to work on whatever you want now.